Hello and welcome back, everyone, to... Actually, not welcome back, because this is something I just made for you guys. You see, I keep playing simulators, but having a bit of coding ability myself, I decided to do a little bit of a fun simulation. So today, say hello to Bob the Blob. He's going to have a lot of children, probably. And let's see how he does. So this simulation is actually using a neural net. I've been working a bit on trying to get working neural net implementations. We'll go a little bit over how I implemented it, but first let me show you, because seeing what's happening is probably the most fun part. So we have two charts. On the left is the inputs, and on the right is the outputs. Now, the blobs can see a few things. They can see walls, they can see food, and they can see other things. But realistically, there's only two things. There's walls and there's food. And the blob has random intelligence when it begins. It may be good at moving around and stuff, it may not. A lot of the time it'll just get stuck. We can see the blob's vision here. Each of those lines is a single thing it can see through. Let's help them out a little bit. Poor thing. Now they start out quite stupid because it's completely random, their intelligence. And you can see the inputs, as I said before, over here, and you'll see they kind of invert, because if it's seeing a wall, then it's not seeing food, and if it's seeing food, it's not seeing a wall. The way it's weighted, though, is that if it sees on the left side of its eyesight, it will go ahead and be negative, and if it's on the right side, it'll be positive. So depending on if it looks at food, it may turn itself. These two outputs are moving forward or backwards, or actually it's just forwards, how fast it's moving forwards, and being able to turn left or right depending on where the blue is. So I can click on different blobs and they have different outputs you'll see for different inputs, and depending on what they're seeing. And that's because every time they get a certain amount of food, they multiply. And when they multiply, they slightly mutate their neural nets. So each of these blobs actually process the world slightly differently. This one over here is doing really well. A lot of them are getting stuck in the corner. But hopefully over time what'll happen is that the ones that don't get stuck in the corner won't die. And yes, they can die. They will run out of food after about 30 seconds. But the ones that don't run out of food will have more children, which should mutate further, and their more successful children should survive and mutate further. So, boom. Oh, it's turning around again. Boom. I mean, the generations are getting very far, and some of these are very fast. I mean, the mutations are pretty small in the weights, but you can see that the different generations definitely have big differences. And sometimes a trait or quality like going super fast will come out, and then a bunch of the children will be super fast for a bit, and then it'll just stop. The next generation will slow down again a little bit because all the fast ones died. But now we're down to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 generations after the stem cell. And you can definitely see that they're getting a little bit smarter. Let's mix it up. All I have to do is go into my code for the cell. All right, and now inside of the code, this is messy. Not going to lie, this is messy code. I was trying to get this done really quickly to make a video out of it. But what we can do is we can go over to the outputs, or actually no, the inputs. The inputs, and we're going to add a new input. This is something I had before, but what I want to add is I want to add the distance to the thing it sees. Okay, so now he should know the distance away that things are. Yeah, that's kind of cool. That's kind of cool. Look at that. So that green there is the distance away that it sees the thing in front of it as being. At least I think that's what that is. Yeah, that's definitely what that is. So let's see if adding that piece of data and giving them one more input to work with increases their ability to survive. All right, guys, enjoy the show. I'll remove myself. Okay, so we've got some interesting behavior here that I'd like to highlight. I believe it's this one has discovered how to unstick itself from the wall. As long as it doesn't die within the next like 30 seconds because this other one is blocking it. Now, they've all come up with some interesting ways to deal with the wall problem. You can see a lot of them use this strategy of wobbling back and forth. Oh, it's gonna die. But this one has figured out that it's actually better if it just turns left. If it continues turning left instead of having a equal back and forth movement, eventually it will always unstick itself. But I think it may be stuck now. Unfortunately, I think its time is up. I don't think it'll survive. Very sad. But all the charts are broken. But if you look, they all are trying to come up with this strategy because it's the most dangerous thing. The food isn't even the issue. Like, there's plenty of food a lot of the time. The problem they are running into is that they run into the wall and get stuck in the corner. It's something that they're not very good at dealing with, and because that is the thing that's killing them most often, that is the thing that is most aggressively being bred for. Like this one right here, you see what it did there? It's so aggressive when it hits a wall about rolling itself back and forth that it's able to get itself out. And part of the issue is actually the way that I set up the eyes to do negative if it's on the left or positive on the right is probably the reason it's doing that wiggling back and forth, because whatever it does for the left is going to be the opposite of what it does for the right. So that might have actually been a bad call. I may make each eye actually have a different input and wait. Oh, look at this one. This one is seriously geared for speed. I don't think we've seen one this fast before. This one is flying. Oh man, look at this. This is an absolute Chad. Look at that. Look at that curve it did. They're really just flying through and bouncing off the sides as quickly and as aggressively as possible. And because of that, as a group, they are getting better at surviving because they're knocking into each other and actually bouncing each other back into survival instead of getting stuck. It's this interesting situation where it's a behavior that's not just good for their individual survival, it's good for all of them. I think it's also probably challenging for them because I'm using physics here. I'm not just shifting them forward. They actually have to deal with the fact that they're accelerating. They can't just stop on a dime, which I think is it definitely adds a bit of a challenge, especially because there's no way for them to back up. But I think this is something I'm going to add. Let's do one last iteration of this where we add another output. I'm going to add... Actually, let's do something fun. Let's make it 3 outputs, and right now, the cells can only move forward by different amounts. But why don't we do something different? First off, for move, I'm going to make it so that it moves by amount minus 0.5f. This is going to make it so that it can move backwards, which is going to be interesting. This is going to make it so that I can move backwards or forwards. And then I'm going to make a new thing, which is move horizontal. I'll rename this stuff and make it cleaner later. And then we're going to do right. And we're going to make it so that they can move left and right as well. This is going to greatly increase the amount of things they can do. Like, a lot. But I'm curious to see what happens. So the number of outputs is now 3. And we have 3 different things it can do. Let's see what happens. I'm curious. I'm very curious to see how this turns out. Oh, this one's moving backwards. First thing it's doing, it's moving backwards. It's probably going to die. I have a feeling it is going to die. It's like, well, time to die. So just moving backwards was just not a good strategy for it. Let's restart and see if we get a smarter one. You know, so, oh, this one just moves left. That's its entire purpose. Oh, it may actually get some food. Crazy. It actually did manage to get some food. But still not a whole lot going on in that brain, and it's probably not going to survive. So let's try again. Let's see if we can get one that at least doesn't immediately die. Oh, this one's interesting. This one is going diagonal. It actually has a little bit of several outputs that are being triggered from the start, and that is probably going to put us in a great position for evolving. Okay, so remember, now they're able to go sideways and backwards, which should mean that the issues that they had before with getting stuck should be easier to solve. There's more tools at their disposal. So I'm gonna go ahead and just let this play again, and let's see if we get some very different output. I'm hoping we get very different behavior, and that they are able to do more interesting things. I can definitely see that they have different strategies. They're children. There's definitely mutation going on here. All right, see you all in a bit. Yeah, so I went ahead and played around a little bit with the food production to test what would happen if I did a really quick population growth and then let them die out. I'm curious if during that rapid growth, if there were any very interesting traits that grew. But as you probably could see, they did a better job of avoiding the walls when we added these additional outputs. And there's a few interesting behaviors that have emerged. I mean, their movement has definitely grown more complicated. I actually could have sworn I saw a few that were purposefully clumping together with other blobs, which is interesting. Oh no, I have absolutely screwed them. evolving so many of them at once and then killing them off, it allowed the weak to survive, giving them so much food. And allowing the weak to survive has left utterly incapable cells. Oh, that one survived! Oh my god. Wow. That was literally almost an extinction event. That was so close. Realistic problem too, if there's a huge jump in population where everyone survives, even if they aren't fit for survival, then when a hard time comes, nothing is prepared to survive, and they have to kind of re-evolve those survival traits, which, as you can see, they're slow and clumping again, which I think I managed to wipe out pretty much how many generations of progress? Many generations of progress. Many. How unfortunate. Hey, it's post-recording Spike, and I don't think I did a very good job on the first try to actually explain how this works. So we're going to go through and do a really quick one-over on how this works, because I think it's important that you guys actually learn something during this time. I had a diagram, but I think it was way too messy, and we're just going to redo this whole thing. So, neural nets are pretty basic. That's kind of what makes them scary. They're so simple, but they're so powerful. They work very similarly to the human brain. So if we look at this, let's say we have 3 layers, and we're just gonna really simplify this for the sake of this video. Let's say we have our 3 inputs. So this is the input layer. And then we have a hidden layer, which I'm going to just have hidden layers. You can have many hidden layers. And then you have output. So these are neurons, but really what they are is they are just mathematical operations, almost basically multiplication and then what's called a sigmoid function. So we put things into the input. So let's say, for example, that we have the eyes. So like this one is food that it might see. This one is wall. And this one is cell for when it sees another cell. So these are the 3 inputs. It can see 3 different things. Let's say maybe it does see food and it's over to the right of the cell. So it's 5. It doesn't see any walls, so it's 0, and maybe it sees another cell to its left, so it's a -2. So now what happens is the hidden layer. You know, the input is just what we put in. Now the hidden layer is neat, because basically the hidden layer is connected. Something you have to remember is each neuron connects to each neuron in the next layer. So they're all connected together. And it's the same thing with the inputs. So this 5 goes into each of these, and this 0 goes into each of these, and this -2 goes into each of these. But these purple lines have what are called weights. So the amount that they affect each other may be different. So like this purple line right here may have a weight of 2 or whatever. So that 5 times 2 will be 10 going into this here. And then this 0 from the second input is going to be a 0, obviously, no matter what you multiply it. But then this -2 from the cell, maybe this line, I don't know if you can really see the one, I'm really trying to highlight it here. This line may have a weight of, 3. So 3 times -2 is -6. So even though it has a smaller input, it has a higher weight, which means it's having more effect on the next layer. Same thing happens through the next hidden layer. And then, if I don't accidentally delete the whole thing like I did right there, just pretend there was still a circle there. Here, let me redraw the circles. Boom. Then, eventually, it goes to the output, and the output does the controls. So you already know because you're watching the video, but in our case, there are two different things that it can do. It can move and it can rotate. When you start these weights all randomly, it means that the inputs will randomly affect the outputs. But what we're doing in this code is we're mutating it whenever a new cell is born. It passes down the weights to the new cell and it changes it a tiny bit. So it'll get better because the ones that suck will die and the weights, which is really genetics of the cell, will be gone forever. So these weights get passed down and they slowly get modified until they make the inputs correctly trigger the outputs. And that way, even though we don't really understand what's going on inside, we don't have to understand what's going on inside of the cell because it's learning. It's just learning on its own. And at the very most basic, if you still don't get it, it's literally just this layer goes to this layer, goes to this layer. If it doesn't cross a certain threshold, it won't go to the next layer. So let's say this is a like 5 and then it doesn't pass the threshold, well then it stops and it doesn't activate the final neuron. But if it does make it through and activate the next neuron, then this one, that maybe there's a weight of 0.5, so now there's a 2.5 in here, and now maybe this one has a weight of 2, so now it's back to 5 in the output. And then maybe the child, it'll mutate a little bit, so this 2.5 will just become a 2.0, and you know math, so 2.0 times 2 is going to become 4. Obviously, this isn't 0.5 anymore because it mutated a little bit. But the point being, when we mutate the hidden layer, the output will change based on the input. You know, you put 5 in, it won't be 5 out anymore. Maybe it's 4. Maybe it went up instead of down. But this is how it learns. This is how it thinks. All right. But I hope you all enjoy watching. This has been a ton of fun. I've really enjoyed working on this and playing around with it. Let me know what you'd like to see added. I'm probably going to play around, add more inputs and outputs, but as a baseline experiment, this works. It really does work. And I'm very happy that it works. Alright, thank you all for watching. Leave a like and subscribe if you enjoyed, and I'll see you all next time.